Okay, question 1. Notice that no matter which animation we pick, the car does the same thing, right? Animation 2, the car is doing the same thing, but the graph is different. So, animation 3, the car does the same thing, the graph is different. Okay, so we got to find the right graph. So first, let's collect some useful information about the car. So we take our cursor tool. Actually, I can't see it. It's hard for me on this screen, but you put your cursor tool right on the center of that red dot, and you get the initial position. And what you should get is negative 1.7 meters, comma, let me just look it up on my other screen, hold on. So these are the values you should get. At the start position, this is x initial, I should have marked it x initial equals, the coordinates are, well, x initial is the negative 1.7. This is the x initial and the y initial. This is the x final and the y final. It doesn't change the y position. That's what we would expect. The x position, the final x position is 2. Let me write it out. So if you write it out, it looks like that. And we're practicing this. And you don't have to write equations when you do Moodle, but you need to practice this. So delta x equals x final minus x initial. That's our equation for displacement. The final is 2.3. The initial is negative 1.7. We subtract that. We get a displacement of 4 centimeters. Okay, let's reset it and run it and see how long it takes to go 4 centimeters. There it goes. There it goes. Let me stop it. Okay, you can see the time. It's 0.88 seconds. So I'm gonna step it. Whoops, I reset it by accident. Let's run it again. '88, '89, '90. Whoops. 94, 96, 98, 1, and then it goes like this. Okay, so it took 1 second to reach there. So the mistake you could make, there's 2 mistakes you could make. Let's run this out. Running it out. Well, runs a long time. Okay, so there's 4 seconds. So first mistake would be to take the 4 meters and divide it by 4 seconds. What would that give you? That would actually give you the average velocity over this interval, which included 2 things. The other thing you could do, and clearly the velocity during this part of the time, nothing is happening. The car is dead against the wall or whatever stopped it. It's only during this 1 second interval that it was moving, and that's the time over which it moved 4 meters. So calculate V average. So there it is, V average is 4 meters per second. Now think about what that is. The thing started going very slowly. At the end it was going very fast. Was it going 4 meters per second the whole time? No, it started probably at 0. And at the end, it had to be going something much greater than 0. So the mistake you don't want to make is this. To get the acceleration, you're going to take the final velocity, subtract the initial velocity, and divide by the time. It went from 0, you got to be careful, is it 0? In this case, it is 0, to some final velocity. How long did it take? To get from 0 to the final velocity, it took 1 second. What's the final velocity? 4 meters per second? No, that's the average velocity. How do we get the final velocity? First, see if you can answer this question of logic. If the initial velocity is 0 and the average velocity is 4 meters per second, guess what the final velocity is. If you guessed 4, you're wrong, because the velocity is always changing. If you guessed 8, you're right. So take 0 for the initial, 8 for the final, divide by 2, and you get your average 4. This is the equation for constant acceleration that also describes the average velocity. And if you do the algebra, v initial is 0. Multiply both sides of the equation by 2, and algebraically you get that v final is 2v initial. That gives you your 8. That's the result that goes into the equation. You want to go v final, which is 8 meters per second, minus v initial, which is 0, divided by the time, which is 1. What do you get for the acceleration? You get 8, notice the units, meters per second, 8 meters per second squared. Now, I'm going to show you another way to get it. Actually, don't be lazy. Go to your equation sheet, look up equation 3, take that equation and solve it for A. Go ahead, do that. Solve it for A, equation 3. This is very useful, very useful. You will use this so many times this semester and next semester. Equation 3. When an object starts from rest, the initial velocity is 0. Whoops, I wrote Vx. It should be Vx initial. And so this term is 0. And then we multiply both sides of the equation by 2. We divide both sides of the equation by t squared, and we get the acceleration as this. So try that. 2 times 4 meters per second divided by 1 second squared. What are you going to get? You're going to get the same thing. 8 meters per second squared. Great. Remember this equation. It will be very useful to you this week, next week, and over the next 2 semesters. Okay, that's a long way around this easy problem 1, but what I just showed you will help you a great deal when you get to number 4. This one is actually pretty easy. Let's run the first simulation. Animation 1. Whoops. Animation 1. Run it. Okay, watch. Stop it. Okay, so you see, this is obviously garbage. Why? Because the initial position is 0, and it should be a negative 1.7. The object is moving, the position is getting negative, so it's moving backwards, but the car is moving forward. And at the end of 1 second, the position jumps from negative 2.3, which is the opposite of where it actually is. It's at 2.3. It jumps back to 0. The car does not do that. So this graph is garbage for a lot of reasons. Let's reset it. Go to animation 2. Play it. Okay, now we're starting at a negative 2.3. We're going all the way up to positive 1.7. Those numbers are reversed. And also the rate at which it's changing position. If you did the graphing MOPS, you know this. This is a straight line, a sloped line up. And if you have a straight slope lined up for the position versus time graph, see if you can follow this, then what does that say about the velocity? It means its position in time is changing steadily. It means the velocity is constant. If it's accelerating, what should it do? So anyway, it's wrong. It starts in the wrong place, it ends in the wrong place, and it shouldn't be a straight line. We'll go to animation 3. Oh, negative 1.7. Oh, it's a parabola. Oh, it goes to 2.3. That's good. and it stays there. It doesn't bounce back. And what we see is it's curved. And so if you did your graphing mops, you know that the position versus time graph for an accelerating object is a parabola. And that's easy to understand, right? Remember the equation we just saw? Delta x was a function of t and t squared. So it's a quadratic function. It should be a parabola. And notice that the slope of the position versus time, right? The derivative of this graph, the dx dt, is the velocity. So notice the slope starts at 0. The slope gets steeper and steeper, and the final slope is here. And the slope here is going to be 0, and the slope here is going to be what? It's going to be 8 meters per second. Meters per second, y over x. There's a lot of calculus and physics in this. So anyway, that's the correct one. Let's see what's wrong with number 4. So what's wrong with that one? Well, it starts at a positive 1.7 and it goes to a negative 2.3, and the acceleration is negative. Okay, question 2. No one's asked me about this, so I think this is probably straightforward enough. Let's play it. So we have an object. As far as I can tell, it looks like it's moving at a constant speed. It's a puck, it hits a wall, it bounces back. Is it moving slower? It looks like it's moving a little bit slower on the rebound. So there should be no acceleration in this problem except for when it bounces off the wall. And but you have a positive velocity going in and a negative velocity going out, and those velocities can be easily measured. So anyway, let's go to the next one. No one's asked me about this problem, so I'm assuming that you all know how to do it. Number 3, actually no one's asked me about this, so I guess you're figuring it out. Let's just play it and see what happens. I have a 0 velocity, so the thing's not moving. So the gate opens, it closes, so the thing had to get through during that time. And then the time's going by, and then you see the other gate opens, and then it closes. So the way I did this, you should try and do it on your own, and then see. But if you've already done it, or then come back and see what I did. I said, okay, it's got to get through the second gate. I'm just going to figure out the distance from the red ball to the second gate and the time, and have it in the middle of the second gate during the middle of the time interval that it's open. So that's one way of doing it. You could say, I want it to be just out of the second gate. You want the back edge to be out of the second gate at the time the second gate closes, because it's got to get through that one, and if that doesn't get it through the front one, then it may be impossible. Or you can time it through the front one, but then you're not likely to get it just right to get through the back one. But maybe it works. But it certainly worked for me. So see if you can, how many times it took you to get it. Of course, you can do this by trial and error, but that's not the point. The point is, so it's not accelerating. You don't have to worry about that. It's just a simple velocity problem. And you can figure the velocity you want to set the Vx at so that it passes through the second gate. It will, in fact, make it through the first gate if you choose that velocity. Okay. Okay, animation 1 is pretty easy because it tells us the velocity, right? And to get acceleration, we want to do v initial V final minus V initial. So 2 seconds. So let's do that. Pretty straightforward, right? The acceleration is that's a minus sign there. So 2 meters per second minus 0 meters per second equals 1 second. You got to be a little bit careful about this 0 meters per second. If you go back and look, you'll see it starts out slow. You can't just assume 0 meters per second, and you'll see that, I think, in animation 3. Okay, let's try 2. We'll play 2. Now, see how it's starting slow, getting faster, faster, faster. Yep. Okay, this one went 1.2 seconds, but we don't have the velocity. Okay, so go back to question 1 where I showed you there's 2 ways of doing this. And let's do it both ways. There's one way, acceleration equals V final minus V initial over t. The V initial 0 because we started out slow, so it looked like it was 0. V final is not V average, so twice V average divided by the time it takes to get from the initial to the final. Be careful about the time. That's 1.2 seconds here. Will give you the answer. And how do you get the average velocity? It's the delta x, delta t. I'm going to leave that to you to calculate. Now, what's the other way? What's the other way? Try it. The other way is to use this rearrangement of equation 3. We did this in problem 1. So go back and watch that. I spent a lot of time on that if you haven't watched problem 1. This equation is very useful. What happened to the V initial, Vx initial t? It dropped out because V initial 0. This only works when V initial is 0. Actually, I'm coming back to animation 2 because there's some useful kinematics concepts that I want to go over. This will be helpful. So let me pause the video. It is really important that you push yourself to understand the difference conceptually and mathematically between average velocity and instantaneous velocity. So an average velocity just averages out a long distance interval with a long time interval. And inside of that distance interval, the thing could be speeding up, slowing down, reversing direction. Anything could be happening. So it's just like a broad average. And it'll only be as good as that. So if we want to know when velocity is changing, it could be oscillating back and forth, it could be speeding up, it could be going backwards and speeding up. What we want to do is we want to look at small segments of it to get what's going on at an instant. And that's so the V instantaneous is you take the rate at which it's covering distance, this ratio or rate of distance to time, and you examine it over a small time interval. And if you do that in the limit that t shrinks to 0, you have what is mathematically the derivative, the ratio of 2 infinitesimal things. Now, how do we do that in the real world? We take a short time interval. So to get the initial velocity, what I want you to do is start at 0, measure the position, and then click the thing and measure the position again. Let me show you what I mean. So you're at 0, and you put your cursor there, and it reads 0, and then you click the 1-step button. You see, I click this button, and it goes 1/100th of a second. What's the position? It's the same. And you click it again, and it's the same. And you click it again, and it's the same. It's still at 0. And what you will notice is you have to click this thing 10 times, 9 or 10 times or more, before you actually see any motion. So that's a good indication that it's starting from rest, right? It really is starting slowly. Now we can do the thing at the far end. If we run the thing out to the end and measure the position, you'll get 1.65. There it goes, 1.2 seconds. You get 1.65. And now step it back 1 step. with the back step button. And it's at 1.19, so that's 100th of a second. That's a pretty darn small time interval. And now measure the position of the cart. What are you going to get? Measure it and see what you get. This is what I got. 1.65 at the end. If I step it back, that 1/100th of a second, it goes back to 1.62. So you see, in the beginning, it didn't move at all for at least 1/10 of a second. And here it moved 0.03 meters in 1/100th of a second. And if you do that calculation, that's our velocity, right? Let me just show you. See what I'm doing? I'm doing an average velocity, delta x, delta t. There's the delta x, there's the delta t. But what? It's a very short time interval. It's like approaching zero. It's not infinitesimal, but it's very small. And so what does this gives us? This gives us a result of 3 meters per second. So what did we calculate it to be? Let's go back and calculate it using the equations. Did you forget how to calculate it? So V final is twice the average, right? Given that V initial was 0. And so 2 times the average, delta x, delta t, or 2 times 1.65 meters over 1.2. And what does that give you? That gives you 2.75 meters per second. You say, but we got 3. It's not the same. Well, answer that question. What's the answer? The answer is the resolution just isn't good enough. We'd have to go to the thousandths of a second. We'd have to have instruments that would measure the distance more precisely and the time more precisely. And in fact, we would get the 2.75 meters per second. Okay, conceptually, all that is very important. Remember that. Okay, now we're ready to go to animation 3. Okay, animation 3, watch closely. You know what to look for. I'm going to start it. See how quickly it started? Now watch it. Does it look like it's speeding up? It may be a little jittery in this version, but anyway, there it goes. So there's no obvious indication of an acceleration. So what should we do? Take the position, back step it once. You see how it moved? Back step it again. And measure the velocity at the end, and then reset it, and forward step it. Here we're going to start. I'm going to use the small step, forward step it. You see it moved right in the beginning. So anyway, if you play around with these buttons, measuring any interval you want, be investigative, be creative, be an experimentalist, you'll see that the velocity is constant. And what's the acceleration when the velocity is constant? The acceleration is 0. It's a negative velocity too, so you want to make sure you get that right. Okay, we can go to animation 4. Okay, here we go. Let's play it. Oh, you see it starts at 0, so we know the velocity, so that's good, but there's no time. Whoops, we don't have a time here, so we can't time it. But if you put your cursor on the red dot, you can get the position. So here you have velocity and position, but no time. Go to your equation sheet, the 4 kinematics equations, look at them, which one are you going to use, and then figure out how you're going to get the acceleration from that. Go ahead, see if you can do that on your own. Okay, I hope you correctly picked equation number 4, this one. Why? Because it has no time in it. It's the only one of the 4 equations that doesn't have the time variable. So you could use the other equations, but this allows you to do it in one step. And Vx initial 0, we don't have to measure that. We're given that when we reset the thing. And Vx final, we're given that directly, the 2.2 meters per second. You do have to measure the delta x. And do that carefully and put it in here, and there's your acceleration. Great. So I just peeked ahead and I noticed the last 3 don't have the time function, and so this is the equation you want to use. Only in one of them, the Vx initial is not 0, so you can't drop that term. You're going to have V final squared minus Vx initial squared when you do the algebra, and then divide that whole thing by the 2a delta x. And in every case, the velocity is given, so there's no uncertainty there. But the delta x you have to measure. And as a final note, in the last one, the object is moving in the positive direction but slowing down. And so the Vx initial is bigger than the final, and you will in fact get a negative acceleration. This is a case that you saw many in the MOPS, where the acceleration, when you slow down, the acceleration's opposite the direction of motion. So if you're moving positive and slowing down, the acceleration's negative. If you're moving negative and slowing down, the acceleration's positive. And you should know that from doing the MOPS. Okay, I guess we're done. Great.